Welcome everybody to Algebra 2, Section 3.1, Absolute Value Functions and Equations. So the absolute value function is written as f of x is equal to the absolute value of x. And a quick reminder that f of x can also be written as y equals the absolute value of x. Now here we're going to be completing a table down right here to graph this function, and then we're going to give the domain and range of the function. Now in this table, it's an xy table, or in this case x and then absolute value of x, which is the y or the f of x. And we're given the x values already. So we're going to plug these into this function up here and get the y values out. So we just take the absolute value of each of these x values. So from top to bottom, we end up getting the absolute value of 3 is -3, so on and so forth down the list. And that's the absolute value of each of these, or the distance from 0 for each of those numbers. And so then as we go ahead and graph these points, we get the following 7 points that we see up here. So for the domain here, the domain is how far left and right this goes, and it goes forever left and forever right. It's all the x values. So you could say it's the real number system, that double-lined R, or you could word it as the negative infinity, comma infinity, because it goes forever left, forever right, everywhere in between, and it's parentheses because it can't actually get to infinity, it's a concept. And the range, how far low and high it gets, down and up, the lowest it ever gets is 0, and it goes everywhere above that, right here, and it goes above. And so that would be like y is greater than or equal to 0, or you could also word it as 0, comma infinity, with infinity once again being a parenthesis, but 0 being a bracket because it's a closed circle. Now this graph, as you may notice, looks like a V. And this turning point right here, the lowest point in this absolute value function, sometimes it's also the highest point, we'll see that later, it's an upside down V, it's called the vertex. Now we're going to be practicing graphing these by tables. We're going to learn another way to graph them in a future section as well. So in order to do this, we create a table of values. And now you notice on examples 1 and 2 here, the x values are not filled out like they were on the table we just completed, meaning we have to figure out which x values we want to use. Now you can use any x values you would like, however your life's going to be easiest if we find the x value of the vertex first and put that in the middle, and then put x values, usually the next integers, lower and higher than that x value of the vertex. And how we find the x value of the vertex, it says in step 1 here, is set the expression inside the absolute value equal to 0, and then solve. Then once again, we're going to place that in the middle of the row box and number up and down to the next consecutive integers, like I just mentioned. Once again, usually we'll see an example today of when you wouldn't necessarily want to do that. And then we're going to plot those points and graph. Then we're also asked to give the domain and range on these problems specifically. So the absolute value of x minus 4. So in order to find the x value of the vertex, I set the inside of the absolute value bars equal to 0. I add 4 to both sides, and I get x equals 4. So I'm going to place that in the middle one. And then above that, I'm going to put decreasing numbers. And above that, and below that, I'm going to put increasing numbers. Once again, I really could pick any 7 values that I want. I just know that it's going to be easiest if we do it this way. We're going to be able to see the most of this graph this way. And I'll show that being the case once we graph it. So if I plug each of these in, so for example, if I plug 4 in here, we end up getting the absolute value of 4 minus 4, which is 0. And if I continue plugging in these different ones, I get down, as I go down the table, 1, 2, 3. And as I go up the table, 1, 2, 3. And I might notice that, hey, the y values mirror each other. Both go 0 to 1, 2, and 3, both down and up. And the same thing happened up here. And that'll happen most times. And specifically, we notice that it happens when this is exactly halfway between the next two values. When it's exactly halfway between the next two values, and it's the same distance as well from like the second value. So 0 to -2 is the same distance as 0 to 2, and so on and so forth with 0 to -3 and 3. And because the same thing's true on the table we just down here, that 4 is the same distance from the next two numbers, or the 2 after that, or the 2 after that, that ends up being symmetrical with the y values there. So as we go ahead and graph this here, we get 4, 0, and then continue plotting the rest of the points. And draw our arrows. I'll draw that a little bit less bad. And that's what we get. Now, you really only need these 3 points. you only need 3 points total, so it could be like the vertex as well as any point over here and any one point over here are the points you want. And once again, the reason we end up using these 7 numbers is because that vertex is the most important point in the absolute value function, because on each side of that, it just continues on forever in the same direction with the same slope. Domain here, we'll notice a theme here that this is again all real numbers or negative infinity, comma infinity, and that'll once again, or not once again, but that'll be 100% of the time the case that the domain will always be all real numbers or negative infinity to infinity for a domain for absolute value functions. The range will be y is greater than or equal to 0. It'll always be greater than or equal to or less than or equal to a number. So in this case, it's greater than or equal to 0 again. It won't always be 0. But 0 comma infinity, with 0 getting a bracket again because it's a closed circle. On to the next one here, number 2. We have to set the inside of the absolute value bar equal to 0 in order to find where the vertex will be, or the x value of the vertex. So I subtract 6 and divide by 2, and I get x equal negative 3. So I'm going to put that value in the middle, and then decreasing values above, increasing values below. And as I plug these in to find out what I get, I'll get 6, 4, 2, 0, 2, 4, and 6. Noticing once again that these y values are symmetrical on either side of 0 or the vertex, because once again, these numbers increase and decrease by the same amount from this. They're the same distance from that x value. And so now as I go ahead and plot these points, I get these 7 points, make the V, and now I do my domain and range. As I mentioned, domain will always be on absolute value functions, all real numbers, or negative infinity, comma infinity. And the range will be y is greater than or equal to 0, or 0, comma infinity. Moving on to number 3 here. The absolute value of x plus 5. So we mentioned above in step 1 for these to find where the vertex is, or the x value of the vertex, to set the inside of the absolute value equal to 0. So that's only the x equal to 0, not this plus 5, because it's outside the absolute value bars. So it's 0 here, increasing numbers below, decreasing numbers above. Plug these in, and as I plug these in, I end up getting 8, 7, 6, 5, 6, 7, and 8. And if you were to evaluate that, you would find the exact same thing, such as like negative 2, the absolute value of that plus 5 is 2 plus 5, or 7, as we see right here. So now as I go ahead and graph these points, we end up getting these 7 points, with the domain being all real numbers, or negative infinity, comma infinity, as it will be 100% of the time with absolute value functions, and the range this time being y is greater than or equal to 5, because that's the lowest point it is 5, and it goes up from there forever, or 5, comma infinity. Number 4 here, as we set the inside of the absolute value equal to 0, and then solve, we end up getting x to be negative 2/3. So as I put negative 2/3 in the middle, you might be wondering, well, what do I put on each side? We'll still pick the next integer. So integers are not decimals or fractions. So the next integer below would be 0, 1, and then 2. And the other direction would be negative 1, negative 2, and negative 3. So now as we go ahead and plug these in and find out these different values, we end up getting the y values of 7, 4, 1, 0, 2, 5, and 8. And you may notice, whoa, these are not symmetrical. Those aren't the same in each direction from the vertex this time. And the reason why is because this is not the same distance from these points. Negative 2/3 is closer to one than the other. And same thing is true for the next two. It's not the same distance from those or the last two, and because of that, the y values are not symmetrical. So we still go ahead and plot this, and even though those numbers look like they're very different than what we've had, the graph will still turn out to be a symmetrical V, even if our points aren't symmetrical currently. So as I go ahead and graph this, I get these points. I graph, or connect them, I should say. And our V is symmetrical even though the points are not. So now our domain, once again, is all real numbers, or the negative infinity to comma infinity. And our range is y is greater than or equal to 0, because that's the lowest point it gets for the y values, and the highest it gets is infinity, or 0, comma, infinity. Moving on to number 5, f of x equals negative absolute value of x plus 1. So that's new, having a negative out there. Let's see how it affects this problem. To find the vertex, it changes nothing. We just have x plus 1 equal to 0 because that negative is outside the absolute value. We only focus on what's inside the absolute value for this portion. So if I solve that, I end up getting x equals negative 1, put that in the middle, and then I'll make my numbers just the same as I have been, where I go the next integers each direction. And as I plug these in now, I notice that after I plug it in, I have to make my answer negative. So all of our numbers are going to be either negative or 0 here. And so from the top of the table to the bottom, I get negative 3, negative 2, negative 1, 0, negative 1, negative 2, negative 3. So that's a new trend, that these numbers are decreasing each direction rather than increasing each direction from the vertex. So as we go ahead and graph it, we'll see that come into play. To where instead of opening up like typical, like a normal V, this one's an upside down V. It opens what we consider down. And so our domain will be unaffected, because as I mentioned, it's always going to be the same domain for absolute value functions, but our range will be affected. Instead of y being greater than or equal to numbers, we're less than or equal to 0 in this case, because the highest is 0 and it goes down. Or if you wanted to write your interval notation, it would be negative infinity, comma, 0. With negative infinity getting a parenthesis and 0 getting a bracket, because that's a closed circle. And we always start with our lower number when we do interval notation, so we started with negative infinity here. Now on number 6 here, or I want to mention real quick on number 5, so the reason why this absolute value is upside down instead of being a regular V is this negative out in front. Anytime you have a negative out in front of an absolute value function, that's what's going to happen. Number 6 here, we have 1/2 x plus 1 inside, so we set that equal to 0, ignoring that for just the moment. So then if we end up figuring out what x equals, x ends up equaling negative 2. So I'm going to put that in the middle. Now, I'm going to write some stuff down, but I'm going to erase it, so I would encourage you not to write it down yet. If I picked my normal numbers at this point, I could still get the correct answers, and it's not wrong. It's going to make our life a little bit harder, because if I plug in a number such as negative 1 here, I'm going to end up getting a fraction, as negative 1 will multiply with this 1/2. And so negative 1 would be over 1, and I end up getting negative 1/2 from that. And while we can do fractions, it's not as ideal. And so if we can avoid it by picking different numbers, it's probably wise for us to do just that, and we probably prefer doing just that. So the question becomes, what numbers could I put in there that would cause this to not have to be a fraction when I actually go to graph this, or get rid of the fraction essentially? And the answer is multiples of the denominator. So like 2 over 1, for example, the 2's reduce. Or if I do 4 over 1, the 4 and the 2 reduce, and it's no longer going to be a fraction I'm having to deal with. And so because of that, I'm going to pick different numbers here, where I'm still picking that same negative 2 in the middle, but as I go above and below, I'm going to pick the next multiple of 2 in each direction. So 0, 2, and 4, and negative 4, negative 6, and negative 8. So this is the only time I really encourage you picking different numbers than the next consecutive integer. Once again, you still could pick the next consecutive integer. You'll just have fractions you have to deal with. So as I plug in these numbers from top of the table to the bottom of the table, I get negative 1, negative 2, negative 3, negative 4, negative 3. I got busy just counting down there. Negative 2 and negative 1. And I go ahead and go to graph this. Oopsie, wrong spot. There we go. And I get these points. And so my domain is going to be negative infinity, comma infinity, or the all real numbers. I wrote that backwards of how I normally do, but really we only need one or the other anyway. And the range would be y is greater than or equal to negative 4, can also be written as -4, infinity. And while I prefer the interval notation myself, I want to give you guys the opportunity to use whichever one makes more sense to you. Now, numbers 7 and 8 use what we call piecewise functions, or they are what we call piecewise functions, and we actually aren't covering that until a later section, and so I'm going to skip those examples for now, and we'll just talk about piecewise functions in later sections, so ignore those for now is what I'm trying to say. So now we're going to go on to absolute value inequalities. So there's only a couple changes here between the equations and inequalities, very similar to how when we solved inequalities, most of our steps in our processes were the same as when we solved equations with a few tweaks. So we're still going to create the table, we're still going to use the vertex, we're still going to graph, but when we graph now, we only use a solid line for less than or equal to or greater than or equal to symbol. So only if it has the or equal to do we use a solid line, similar to how the equation, which was an equal sign, had a solid line. But now if it's a less than or greater than, no or equal to, we only use a dashed line, and we'll see that. And then our third step is we have to shade here, and I'll just talk about more of that when we get to that step rather than reading it all out now. So on number 1, y is less than the absolute value of x plus 1. So for a moment, we just ignore all of that, and we focus on this. We'll get to the rest of it later. And so as I do the absolute value of x plus 1, I say, well, the inside of the absolute value bars, set it equal to 0, I get x equals -1, and that's what I put in the middle. I pick the same numbers I would normally, where I go to the next consecutive integers. And as I plug them in and get my numbers out, we're not being concerned about it saying y is less than, but just figuring out, hey, what would I get from the absolute value here, or from anything on this side as I simplify. I end up getting the numbers from top of the table to bottom of the table, 3, 2, 1, 0, 1, 2, 3. And I plot these points like normal. So as I go plot these points, -4, 3, and so on and so forth. Now here is where the change comes in. So I look back now at this inequality and I note, hey, that is less than. So because it is not or equal to, we do not use a solid line. Instead, since it's just a less than or a greater than symbol, we use what we call a dashed line. So as I go down here, I will use a dashed line. So that's one change that we do for inequalities versus equations. The other change is step 3, where we shade. So we're not just saying we want the v here for the absolute value, whether it's right side up or upside down. That's not what we're looking for on the graph necessarily. We're saying that we want the y values that are less than that. Now for y values, less means lower and greater means higher. It means as you go down the graph, those are the lower y values. And as you go up the graph, those are the bigger or greater y values. So y is less than the absolute value of x plus 1. I'm going below this graph, and so I just shade that in. And now it doesn't have to be perfect. I'm not going to be making sure, oh, you got everything, and you have to stay exactly in the lines. Like, I'm not a coloring teacher here. So if you shade below it, I'm going to be happy as long as I can tell, hey, that's where you were shading. And so for this, we're saying, hey, these are all the values that fit this criteria. They are less than this dashed line. So we're talking about all of these numbers, but not this line or not anywhere above it. So once again, really the two changes here was, since we did not have an or equal to, we just had less than or greater than, we did the dashed line versus a solid line, and then we shaded accordingly for whether y was less than or greater than those. So on to number 2 here. Once again, set the inside equal to 0 of the absolute value bars, just kind of ignoring that for a moment for the y is greater than or equal to. And we end up getting x equals 5. Put that in the middle and put my numbers accordingly on each side of the 5, above and below. And as I go through and evaluate, I get 1, 0, -1, -2, and then I start going the other direction. And I go and plot these. And now is when I bring into play this inequality symbol. It is an or equal to, so I'm using a solid line just like I did for my equations earlier. Similar to the open and closed circles that we used when we graphed inequalities, like y is greater than this number when it wasn't an absolute value function. And then now we're saying y is greater versus less than. And so the numbers that are going to be greater are going to be the ones that are higher, above. So we're shading up here somewhere. And I'm not going to make sure that like, oh, you know what? It goes over here and you actually went over here. I'm not concerned about that, okay? On number 3 here, y is greater than the absolute value of 4x plus 6. So I take 4x plus 6, I set it equal to 0, I solve, and I get x to be negative 3 halves. The next number greater is negative 1, 0, and then 1, and then less would be negative 2, negative 3, and negative 4. And the y values, as I plug these in, I'd encourage you to plug them in on your own if you haven't been already, and then figure out what they would be, but I will tell them now are 10, try that again, 10, 6, 2, 0, 2, 6, 10. And he made it as, hey, well, these are symmetric again, but last time we had a fraction here, they weren't, okay? Well, here's why. Because negative 3 halves is the same distance from those two numbers, negative 2 and negative 1. And it's also the same distance from negative 3 and 0, as well as from negative 4 and 1. Where earlier it was negative 2/3, which is not the same distance from the next consecutive integers. So as I go ahead and plot these points, negative 4, 10, and 1, 10 obviously go off the graph. So you can just go ahead and elect not to graph them. If you want to graph them, that's also fine. It's not really a concern one way or the other as far as I care. And because it's greater, not greater than or equal to, it's a dashed line. And then we shade above because it's greater than. These are the y values that are greater than it. So greater means higher for y. Number 4, y is less than or equal to negative absolute value of 2x plus 3. So it is negative, so it should be opening upside down this time, so take note of that. So as I set the inside equal to 0 and I solve, I get x to equal 0. And I'll put my other x values accordingly, just the next integer. Remember, the only time we did something different than the next consecutive integer was when there was a fraction multiplying with the x, and then we just picked multiples of the denominator. So as I go through and find my y values, I get negative 3, negative 1, 1, and 3, and then I just go back the other direction and have the same numbers I had as up above. And I go ahead and plot this. And because it is an or equal to, this line is solid, not dashed. And then it's less than versus less than or equal to. So we're going below the line. So this happens to be inside of the V. Even the last one was inside the V because this one was inside the V because that's above. This one's inside of the V because that's below or less than. So whether or not we're inside the V or outside of the V, it only is determined by whether we're above or below and which way the V is facing. So don't think of it that way if you were before. Only think of it as above and below rather than inside or outside. I don't know if anyone was thinking about it that way as far as we're in the V or we're out of the V. That's an inconsistent way to think about it, or think about it that way, I should say, will lead to inconsistent results. All right, number 5. The absolute, or y is greater than or equal to the absolute value of 2x minus 12 minus 7. So set the middle, or the absolute value bar is equal to 0. Solve that, and I get x to be 6. And then I pick my next consecutive integers, noting that 9 will go off the graph, and that's fine by me. And then I plug in my x values and get my y values out, and I get negative 1, negative 3, negative 5, negative 7, and then I just mirror those same numbers up above. I go to graph this. And I could try to graph this point, or I can choose not to graph that point. It really doesn't matter. Oh, this is a solid line. I graphed it before thinking through that. A good thing I got it right accidentally. And then I will shade above because these numbers greater than it, as we're mentioning. Last example of the day, negative. So I'm going to clock that. Notice that this goes upside down. Okay. Set the inside equal to 0. Solve, and I get -3. So I put that in the middle. And then numbers bigger and smaller. And then as I plug these in, I get the following y values out. -5, -2, +1, 4, 1, -2, -5 again. And so I go to plot these points. And then, oh, sorry, that should be a dashed line because it is not or equal to, it's just less than. And then I'm going to go less than, so it's below this graph. And that wraps up Algebra 2, Section 3.1.